Hello! In this video, we are going to prove the following theorem. Let A, B, and C be sets, and suppose f is a function from A to B. Suppose C has at least two elements, and for all functions g and h from B to C, if g compose f equals h compose f, then g is equal to h. Then f is surjective. Now, before we get into proving this theorem, let's do some scratch work. Now notice, we're trying to prove that f is surjective. What does it mean for f to be surjective? It means that for all elements y and b, there exists an element x and a such that f of x is equal to y. So to show that f is surjective, we can try to prove this statement. Well, we're trying to prove a statement about every element in B, so give me an arbitrary element of B. I'll call it y. And from here, we're trying to show that there exists an element x and a that satisfies f of x equals y. And in showing this, we're going to need to somehow apply the fact that C has at least two elements. Well, since C has at least two elements, this means we can pick out two elements in C that are distinct. I'll call them P and Q. But also, we need to apply the fact that for every two functions from B to C, this is true. Now, we aren't given any function from B to C at all. So in order to apply the statement, we're probably going to need to construct functions from B to C ourselves. Well, what happens if we will have constructed two functions from B to C? Well, if we have two functions from B to C, we will be able to say that this statement is true. So we will have that if this is true, then this is true. But it's actually probably going to be more useful to use the fact that if this is false, then this is false, right? It's probably more useful to use the contrapositive, because if we end up constructing two functions from B to C where this is false, well, by the contrapositive, this tells us that this must then be false. And what does it mean for this to be false? Well, we know that g compose f and h compose f are both functions from A to C. So to say that these two functions are not equal means that there is at least one element x in A such that g compose f of x is not equal to h compose f of x. So we will have found an element in A. Maybe that's the element in A that we're looking for that satisfies f of x equals y. Right, so in the long run, if we will have identified an x in A such that g compose f of x is not equal to h compose f of x, well, can we show that this is the x that satisfies f of x equals y? Well, we know that g compose f of x is the same thing as g of f of x. And similarly, this is just h of f of x. So this is really what we have here. But the intention is that f of x is equal to y. Well, we need g and h to be functions so that this implies that f of x is equal to y. So maybe at this point in the argument, maybe we assume for a contradiction f of x is not equal to y and get a contradiction. What might that contradiction be? That contradiction might be that g of f of x equals h of f of x. And so these two contradict each other, which means this assumption would be wrong. And so we must instead have that f of x is equal to y, which is what we want. But we need to construct g and h in such a way that we obtain the ability to arrive at such a situation. So how can we do that? Well, since we're expecting f of x to equal y, this means we must have that g of y is not equal to h of y. But when we assume for a contradiction f of x is not equal to y, we should arrive at the situation where these two contradict each other. And the way we can make that happen is we can make sure that every element t in B that is not y, when we send t into the function g and h, we get that g of t is equal to h of t. If we constructed g and h so that g and h satisfy both these conditions, we should expect this argument to follow. So then what should we define G and H to be? Well, we can define G so that we send every element in B to the same element in C. So we'll take every element in B and send it to P. As for our function H, we'll send Y to Q, and we'll send everything that isn't Y to P. If we define G and H in this way, then G and H satisfy these two conditions. Because, well, we see that G of Y is just P, but then H of Y is equal to Q. So clearly G of Y is not equal to H of Y, right? Because P is not equal to Q. But if we give ourselves any element T in B such that T is not equal to Y, well, G of T is equal to P, H of T is equal to P. So G and H satisfy both these conditions. So we should expect this argument to follow. So this completes our scratch work. Now let's get into the proof. Now to prove F is surjective, we're trying to prove this. Well, since we're trying to prove something about every element in B, give me an arbitrary element in B. I'll call it Y. Now let's apply the fact that C has at least two elements. This means that there are two elements, P and Q in C, where P is not equal to Q. Now, let's define our functions G and H. Now, something I didn't mention in the scratch work is, based on the way we defined G and H are indeed functions from B to C. Because it is true that for all elements I and B, G of I is an element of C. And it is also true that for all elements I and B, H of I is an element of C. Right, I'll leave that up to you guys, but we don't really have to show that. But anyways, now that we have functions G and H from B to C, it follows that if we apply this statement, that if this is true, then this is true. In other words, by the contrapositive, we know that if this is false, then this is false. And we want to use the contrapositive, right? We want to show that G is not equal to H, so we can conclude that G compose F is not equal to H compose F. So let's show that G is not equal to H. How do we show that G is not equal to H? Well, we need to find at least one element, X, in B, such that G of X is not equal to H of X. Well, we're going to show that G of Y is not equal to H of Y. To see how, well, note that G of Y is equal to P, and H of Y is equal to Q. Since P is not equal to Q, it follows that G of Y is not equal to H of Y. So, there exists an element in B, namely Y, that satisfies G of Y is not equal to H of Y. And that tells us that G is not equal to H. And then we can apply the contrapositive of this statement to conclude that G compose F is not equal to H compose F. In other words, there is at least one element X in A, such that G compose F of X is not equal to H compose F of X. Now we know that this is just G of F of X, and this is just H of F of X. Right, and this is the point where we want to show that F of X must be equal to Y. And show that, well, assume for a contradiction F of X is not equal to Y. Well, if F of X is not equal to Y, then when we take F of X and send it into the function G, well, yeah, G of F of X is equal to P. And when we take F of X and send it into the function H, well, since F of X is not equal to Y, we must have that H of F of X is equal to P. So G of F of X equals H of F of X. But this contradicts the fact that G of F of X is not equal to H of F of X. So our assumption that F of X is not equal to Y led us to a contradiction, so we must instead have that F of X is equal to Y. So as you can see, there exists an element X in A such that F of X is equal to Y. Namely, if we take X here to be the X in our proof, Well, yeah, x is an element of A. That's what we have here. And f of x is equal to y. That's what we have here. So we have shown that this is true. Since y was arbitrary, this means for all elements y in B, this is true. So this tells us that f is surjective. And that is exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.